material, it is a positive bound charge. Now it is a positive bound, it is surrounded by donor. This is nothing but your electron. Now see, this is what I am drawing here. Now here it is p type is negative ions, it is having holes are the majority carriers. In type it is positive ions which is surrounded by the electron. This is one electron and another electron, one electron, six, like this. Here electrons are majority charge carriers. In this side holes are majority charge carriers. Okay, here along with the holes, some of the electrons also present in the p type, minority charge carriers. In case of n type, along with the majority charge carriers, electrons, some holes also present here. Now the thing what I am saying is, in p type material is having the negative ion which is surrounded by the hole. The positive ion is there which is having the donor atom, that is your electron. Like this it is having the plus surrounded by your electron, two surrounded by your holes. I am not drawing the complete this portion. This is in this way the p type and n type material will be. Now the first initially if I am not applying ion on the p type material, now what is going to happen? Now here the negative ion is there with your hole here. Here the positive one surrounded by the electron here. Okay. Now these electron and the hole, these will be very near. Now what is going to happen? This electron and hole pair recombination will take place, that will disappear. Now what is there in this portion, in this part? In this part, now all this electron and this hole recombination takes place. Here this electron and this whole recombination takes place, and here this electron, this whole recombination takes place. Whenever electron hole recombination takes place, that is leaving an ion here. That means it is leaving a negative ion this side and the positive ion this side. Now in this area we are not having any charge carriers. That means there is no electrons and there is no holes. Now what are the present in this area? In this area only immobile ions are there. These ions are not movable. These are immovable ions are there. In the n side positive ions are there. In the p side negative ions are there. Now that is the next slide. See here. In this slide, I am not shown you that ions. Here I have taken only this holes. Holes are the majority charge particles in the p type, electric charge carriers in the n type. Here I am not showing the ions. Now in this depletion region, how we got these ions? After recombination, whole pair recombination, they are leaving the immobile ions here. Now, like this, here also one positive ion is there surrounded by the electron like this. This is a representation of n type and p type material. I hope it is clear up to this. Now, if you combine the p type and n type material, the depletion region is going to be formed. Depletion region in the sense, in this region there is no charge carriers. All the charge carriers are depleted. Okay. Now, this side electron and this side holes, they cannot recombine because there is a region. The depletion region is there, like we can say there is a wall is there between these two materials. Now this electron cannot move to this area because these electrons are not having that much energy to cross the junction and to enter into the p type, or this hole is not having that much energy to cross enter into the n type material. Now that's under the no bias condition. Under the no bias condition, now simple depletion region is going to be formed. In this depletion region, there is no charge carriers present. Only the immobile ions will present here. This is just I'm combining a p type and n type material. Now this is what is there in the steady state. In the steady state, it's a p type material and it is an n type material. Now this is a space charge region. That is nothing but your we are calling it as the simple depletion region here. Other name of depletion region is space charge region. We may call this. This yesterday I discussed here. Once again, we will see this in detail. Right. Now at t is equal to 0. Now what is at t is equal to 0? take three scenarios. First scenario is just I combined N-type material and P-type material. Whenever you combine P and N-type material, immediately what is going to happen? The P-type free holes are there. In case of N-type, free electrons are there. Now see here, in this, the negative is nothing but the minus symbol is electron, plus symbol is a hole. These are not ions. Ions are always surrounded by the circle. In this diagram, ions isn't. Now in the P-type, what are the ions? Negative ions will be there here, immovable ions. The N side, the positive ions will be there. But in this picture, we are not considering the ions. We are taking only majority charge carriers because majority charge carriers will plays the major role for the constitution of current. That's why in the N-type, majority electrons, the negative is the minus is nothing but electrons. In the P-type, holes are there. Majority holes are there. At t is equal to 0, what is going to happen? Now see, this hole and this electron will recombine because these will be side by side. They can easily recombine. Externally, no need to supply any energy from the P side or N side. Now see, this one and this one also will this one recombine will easily, and this hole and electron, these will recombine. Whenever these electron and hole recombination will take place, now what I said, it will leave an immobile ion. It will leave a positive ion in the N side. It will leave a negative ion in the P side. These ions are not surrounded by the charge particle. That's why these are the positive donor ions, these are calling. These are the negative acceptor ions for P type. Now in this region, now see I am drawing the two vertical lines. In this region, charge particle means positive and negative charge particles are they recombine. There is no charge particle in this region. All the charge particles are depleted, calling as a depletion region. At t is equal to t1. The t may be, for example, 1 second time, or it may be some 500 milliseconds time. Within that time, now there is a recombination will takes place. Depletion region is going to be formed. At t is equal to infinity, in the sense after 5 minutes of time. For example, it is immediately combining N and P type material. It is after combining after 1 minute of time. I'm assuming, just I'm assuming. Now it is after 10 minutes of time. Now, after 10 minutes of time, what is going to happen? Now, whenever you are combining, depletion region is going to be formed. After some amount of time, even though you are not supplying any energy, now this electron, this hole, that means this hole and this electron also recombination will take place. That means the energy is sufficient to recombine these electron and hole. Now that's why what is going to happen, this depletion region width is going to be increased after some amount of time. But don't consider this part. Now generally at t is equal to t1, this initial will consider only this is the width of the depletion region. Under the biasing case, we are going to discuss about the third one. Now what is this? As free electrons and holes diffuse across the junction, a region fixed ions is left behind. This region is calling as our depletion region. Now this is nothing but our depletion region. Right. This open circuit junction, the P-type material is nothing but region. Now, how the band structures will be looking like in case of P-type and N-type material? In the P region, what are the majority charge carriers? Holes are the majority charge carriers. Now, where the holes will present? All the holes will present in valency band. That's why the height of the valency band is very, very large compared to your height of your conduction band. Now, in case of p-type, the valence, half of this you are considering as a Fermi level. This is a Fermi level. The Fermi level is it is near to the valency band in p-type material. Now, what about n-type material? In case of n region, there is large number of electrons are there. Now, where the electrons will reside? Generally, these excess electrons they are forming as a donor energy level, and at the room temperature, all the donor electrons will be moved to conduction band. Now, in N region, the conduction band is very, very large compared to the valence band. Now, if you take the Fermi level is here near to the conduction. That means these are very important objective questions. In case of p-type material, a Fermi level will be near to which band? That will be valence band. In Fermi level will be near to conduction band. This is a band bending structure we are calling. Now, it is at the open circuit case. That means I'm not applying any voltage between the P and the N-type material. I'm not applying any external voltage to the P and N-type materials. In the open circuit condition, this is a band bending structure of P-type and N-type regions. Now, what is the same thing in the no applied bias? If you are not applying any bias, Vi is equal to 0. 0 means I'm not applying anything here. Simply the structure will be looks like this. Okay, at this 0, you are not applying any external voltage. Majority holes will be there in valency band. In case of p-type material, all electrons they are going to be there in conduction band for the n-type materials. Now, any electron or hole that wanders into the depletion region will be swept to the other side via the electric field. Now, see here, just I am explaining. Now, for example, now this side is nothing but our p-type region, and this side is nothing but we are calling our n-type. I am taking only this conduction band portion. Look into these two. Now, for example, in the N region, majority charge carriers are electron. If I want to move an electron, for example, electron is there here. Now I want to move this electron to the p side. Is it possible in this case? In this case, it is not possible because when the electron can move very freely, now if there is no barrier, this is I'm calling as a barrier. That means if the band will be like this, if it is a p-type band, if it is n-type, both will be in the same line, then the electron can move easily from the n-type to the p-type. But in this case, electron is in this, I mentioned this electron is at this place. Now this electron cannot enter into p side because it is here conduction band is at this level, band is electrons at this level. Now what we have to do now, if we are able to decrease, that means we are able to move the conduction band up to this point. For example, the conduction band is at this point, then this electron can easily move to the p-type region. Now that we can achieve with the help of biasing concept. What is the biasing? Forward bias, reverse bias is there. In case of forward bias, by applying an external voltage, we are making this. It is a band bending. This is a bending structure will be there. Now we are making this band bending structure to the flat structure. If it is, the electrons can move freely to the p side, the holes can move freely to the n side, and the electrons and holes are moving. That is constituting the current. The maximum current we can obtain in the forward bias case. That we can see in the next slide. So this is a case. Now here this is a barrier is there. Due to this barrier, this electron directly cannot enter into the p side. Okay. Now we have to reduce the height of this barrier. If you are reducing this height of this barrier, then these electrons and holes they can move very freely. Now see the first one is biasing the p-n junction. This is a forward bias. Now forward bias is nothing but by connecting an external supply, by connecting the positive terminal to the p side, negative terminal to the n side. Now remember this. Now if you are not connecting any voltage source, now ideally this is open circuit p-n junction case. Now if you bias the p-n junction with the help of external voltage source, now in which fashion? Now when an n-type region of a diode is at the lower potential, that means n-type is connected to the negative terminal, the p-type is connected to the positive terminal. This connection we are calling as forward bias connection, FB connection is a forward bias. The forward bias, the positive terminal is connected to the p side and p to p. That means positive to the positive side, p type. Negative terminal to the n type material. If it is positive is to the p type, negative terminal is to the n type, Now this arrangement we are calling as a forward bias arrangement. Now what is going to happen in forward bias if you are connecting the voltage source in this fashion? Now the width of the depletion region will reduce. How it will reduce, we'll discuss now. Now this is the positive polarity. Now from the positive polarity of the battery, now what type of charge carriers will come? It's nothing but your holes will come. The hole is nothing but positive charge carrier. All this is generating the holes, and these holes are injecting into your p-type material, because from the positive terminal the holes is going to generate the holes. These holes, they are entering into the p-type region. Okay, now from the negative terminal of the battery, now what it can generate? The electrons. It will come the electrons. These electrons, they are entering into your n-type material. Now see, now from this external battery source, positive terminal, from the positive terminal, all the holes are entering into the p side. Now in the p-type material, already holes are the majority charge carriers. If I am assuming here it is the 100 holes are there. Now with the external battery, now one more 100 is entering into the p-type. Now what is going to happen? This external, this already 100 holes are there. Along with this 100, for example, these 100 holes, they are creating some electric field. One more extra 100 entering into the p-type material, that is making doubling the electric field. Now that means these electrons, so externally, that means battery voltage. For example, voltage is 1 volt you are applying here. For the 1 volt of supply voltage, it is generating the 100 volts. You are applying the 5 volts at the battery. Now more and more positive voltage you are applying, more and more holes it is injecting into the p-type region. Now due to this, now what is going to happen? Due to the external electric field, now these holes, they can cross the depletion region and they can enter into n-type, because these more and more holes, now the depletion region width is going to reduce, because these are already 100 holes are there here. These holes are coming nearer to the junction, and for example at the 1 volt power supply, if I am applying the 1 volt battery, for the 1 volt, these hole it can move to this side. What I am doing, externally you are forcing the hole to move to the forward direction. This is the forward direction of the hole. Now this is the forward direction of your electron. Now these excess electron, that is pushing the electrons towards the junction, the forward direction. These excess hole, that is pushing the holes in this forward direction. For this holes, it is a forward direction. Now as a result, what is going to happen? Now previously this is the width of the depletion region. Now due to the external battery voltage, now this width is going to reduce, and due to the external supply voltage, these holes, they can cross the junction and they can move to n region, and these electrons, they can cross the junction and they can move to the p region. Now this type of arrangement we are calling as a forward bias arrangement. Forward bias is nothing but these electrons, they are moving in the forward direction. These holes also, they are moving in this direction, forward direction, from this side. Okay, as a result, what is going to happen? Now here, so majority electrons are there in the n material. These majority charge carriers, they are entering into the p type. All the majority charge carriers, they are entering into the p type, and it is becoming the minority charge carrier here. Okay, and now one more thing is there. Another way I can discuss here. Now I hope this is clear in the simple way. What is the arrangement of forward bias? In case of forward bias, the positive terminal is connected to the p side and the negative terminal is connected to the n side. Now this arrangement we are calling as a forward bias. In forward bias, the width of the depletion region will decreases. As a result, this majority charge carriers, they will move from one side to the another side. The charge carriers are moving from one side to another side, means that is causing the that is constituting the current. That's why maximum amount of current will flow in forward bias, because maximum number of electrons, they can cross the junction and they can come to p type, so that it is constitute the current in opposite direction, that we are calling as the diode current. In case of forward bias, diode current ID is maximum amount of current will flow. It is ID is maximum. Right. Now I will explain another way this, the same concept I will explain. Now, now this is our NP junction. This is our N-type material, and this is our P-type material. Now, what is the forward bias arrangement? In forward bias arrangement, N-type material is connected to the negative supply, P-type is connected to your positive terminal. Now, this is a forward bias arrangement. Now, in the N-type material, electrons are majority charge carriers. The P-type material, holes are the majority charge carriers. Right. Due to this external voltage, now this positive terminal is, it is injecting the holes into the P-type region. Now, P-type is already majority holes are there. Along with this majority holes, externally also due to this external supply voltage, more number of holes are entering into the P side, and it is becoming the more and more positive. Now I can say this is at the positive side. All the holes are having the positive charge. Due to this external holes also, it is becoming more and more positive. That means maximum positive electric field is going to be developed across the junction at the P side. Now this becoming more and more positive. Now how it was become more and more positive? Because of connecting externally positive terminal to the P side material. Because already P type due to connecting the positive supply to the P type material, it is becoming more and more positive. Now it is more and more positive is there. Electric field is there here. Now it can attract the electrons. Now this side also majority number of electrons are there. More and more electrons are there. Called parallel press. Now this is becoming as a more and more positive. This is becoming more and more negative. Now if one side positive is developing here, it will attract the all the electrons at this side. That means the electrons present in the N region, it is attracted to the positive side of p-type region, and they can move to this way. So all the holes will be attracted to this plate. It's becoming as a minority charge carriers in this region. See, the two ways you can explain the forward bias. The first thing, why the maximum current will flow in forward bias. First thing is arrangement is clear. What is the forward bias arrangement? Now connecting the positive terminal to negative forward bias. Now in the forward bias, the width of the depletion region is going to reduce. Now, if the width of the depletion region is decreases, now so that the charge from one side to another side means the maximum amount of current is going to produce. That's why in the forward bias, maximum amount of current is going to be occur. Now see, the depletion width is shortened and the built-in electric field is decreased. Now already in this region, some electric field is already produced. That I said there is a built-in electric field going into P, and they can easily cross from P to the N side region. Now this I will explain with the help of band diagram. Now see, when a diode is connected in forward bias condition, what is the forward bias condition? Negative voltage is applied to the N-type material, positive voltage is connected to the P-type material. That is the arrangement of forward bias. If this external voltage becomes greater than the value of the potential barrier, that is 0.7 volt for silicon and 0.3 volts for germanium. Remember, these are the minimum voltage required to turn on the device. For example, if you diode, the minimum amount of voltage you are going to apply is nothing but your 0.7 volts. Up to 0.7 volts, there is no current. That volts only the current conduction will be takes place through the diode. That is a built-in potential. And now this is 0.7 volts for silicon and 0.3 volts for germanium. Now, what is in forward bias case? Now, in the open circuit condition, now see, this is the open circuit condition. In the open circuit condition, the height of the barrier is, see, this is the height of the barrier. This is a now, see the height. Now, this is the height of the barrier. Due to this height, the elements and the hole, they are not able to move from P to N region and N to P region. If you apply an external voltage, what is going to happen? The barrier height is going to be reduced. So now see the height of the barrier. Only this is the small height. This is only these electrons. See the top electrons, they can easily move here, and this also that can easily move here. Now, if you want to move the maximum number of electrons by, for example, if Vi is equal to, now this is a condition for Va less than 0. Less than 0 means your supply voltage is applied, but it is not less than 0.7. If I take the less than built-in potential, this is the case. Now, if you apply the 2 volts or if you apply the 3 volts or 5 volts, this structure will come very straight fashion. That means the P type and N type, this will come in straight. All the electrons, the holes, they can move to the M side. Now, see the statement here. In the forward bias, the barrier is reduced. The height of the barrier is reduced. So, more electrons and holes across the junction. Holes from the P type, they can diffuse to the N type. Electrons from the N type, they can diffuse to the P type. Now, why I am using the word diffuse? Because there is a large concentration gradient. In case of N type, electrons are maximum. In case of P type, no. Concentration gradient. Here, maximum electrons are there. Here, minimum electrons are there. Due to the concentration gradient, now these electrons, they can move to the P side. At the same time, these P in the P material, holes are maximum number of holes are there at the P side. Here, the minimum number of holes are there. Due to the concentration ingredients, now these holes, they can move to the N side. Now that's why the movement is due to the concentration differences that we are calling as a diffusion current. Now these electrons, these holes are, they are diffusing. Now increasing the Va. Now if you increase the voltage, now the electrons and holes that have sufficient energy in an exponent. Now so that these all the electrons, they can move to the P side, all the holes, they can move to the N side. The drift current is going to be remain in the later. It's for the forward bias PN junction case. Now, what is the forward bias condition? In case of forward bias, now this is the minute. Is my voice is clear? Voice breaking. Okay, now voice is still, it is not audible. It is breaking from long time. Actually, if I open the PPT, the chat box is, it is automatically, it is hiding. Now when I come back to the main screen area, then only chat box is visible to you people. I am not closing this chat box. I am keeping this, it is open only. But if I open the PPT is overriding the chat box. Okay, now also it is clear. Now also chat box is open to you, but now the PPT is not visible to you people. People are able to see the presentation. Okay, if we increase the voltage, then only the diffusion takes place. Yes. Okay, okay. Already I know this. I can move the chat box to the left side. Already I got the full clarity about the chat box also. Okay. Now my voice is clear. Now, I adjusted in the orange box only. Here only, chat box is here only. Still it is breaking. Why? Now it is visible. The chat box visible to you. Okay. Now I will keep the chat box as it is only. Okay, right. Right. In forward bias, just we are applying external voltage, the positive polarity, positive terminal to the P side, the negative terminal to the N side. Still voice breaking. Now, okay, clear on. Okay. Now this is the case. And now we go for the reverse bias. Now what is going to happen? Now, in case of, just I will draw here once again, just to briefly I will explain. This is a forward bias case. In case of forward bias, if you are increasing the voltage, if you increase the supply, now what is going to happen? These electrons, they can move easily to the P side. Because the depletion, that means the width of the depletion region was decreased. So that's why these electrons, they can diffuse from the higher side to the smaller side. That means due to the concentration differences. Now, electrons, majority electrons, they are moving from N side to the P side due to the concentration difference. That's why the current is due to the diffusion of the charge carriers. This current we are calling as the diffusion current. In forward bias, the current is due to the diffusion current or diffusion of electrons only. That's why the width of depletion region decreases. Now that is what I said just now. Now see here. Now this is your P-type material and this is your N-type material. You combine the P-type and N-type material. Now initially this is the width of the depletion region. Now in the N side you are having the negative ions are there. The negative ions are there. The P side, these are the positive ions are there. Immobile ions are there. And the P side, holes are the majority charge carriers. I am taking positive is nothing but your side. Electrons are the majority charge carriers. That only I am telling. why the width of the depletion region decreases. Which one is reverse? These are surrounded by the circle. Now here I am drawing only the electrons. It's a negative means electron, positive mean hole. If the positive is surrounded by a negative circle means that is a negative ion. P side negative ions are there. Oh sorry, this is the negative ion this side. Okay, and this N side you are having the positive ions. Right. Right. Now, why this width of the depletion region will decreases means now if you connect a voltage source between these two terminals in such a way that N type is connected to the negative terminal, P type is connected to the positive terminal. Now, this positive is from this holes are going to be generated and these holes are injecting into the P side. Already P side we are having the majority holes are there. Now, apart from these holes, still more number of holes they are injecting into the P type, and so that these, due to the external electric field, this is external electric field. Now these holes they can move, enter into the depletion region. That means this can move from this place to this place, and due to the external and negative supply from the negative terminal, electrons are coming. Due to this external negative voltage, these electrons they can move from this place to this place. That means in this case, the width of the depletion region is becoming very, very narrow, very small. The width of the depletion region is small. How it is becoming small? Due to the external supply. Externally, you are applying the voltage. That means you are forcing the hole to move in this direction. The positive and positive both polarities are going to be same, going to be well, and the opposite charges they are going to be attract. Now, this positive charge, these positive charges and these whole electrons, this external voltage will make these electrons to move in this forward direction. Now these electrons also vice versa, it is going to move in this direction. Because of this, the width of the depletion region is going to be decreases. Now the width of the depletion region is very, very small, then the majority charge carriers they can easily move from one side to the other side. I think there is a problem with your local problem is that the voice problem. Now at your internet side, everyone is getting the same problem. My voice is no. Now don't type the voice is breaking like that. Now check your internet connection. Now this is the main reason, the forward bias due to the external voltage. Majority electrons they are moving from one region to another region that constitute the current, that is the diffusion current. In forward bias, the maximum current will conduct. That current is due to the enough charge carriers. Now come to the reverse bias. Now reverse bias is the different scenario. Now what is the reverse bias? Now if you connect the positive terminal to the N side and the negative terminal to the P side, this arrangement we are calling as the reverse bias arrangement. Now in the reverse bias, what is going to happen? Now this positive terminal is from here, what we are getting? Now you are getting the holes, positive charge carriers are coming. These positive charge carriers are coming. This is the positive charge carriers are coming from the positive terminal, and from the negative terminal, negative charge carriers. Now these positive charge carriers they are entering into the N side. Negative charge carriers they are entering into the P side. What is going to happen? Initially, before this is the width of the depletion region I'm assuming. Now due to this opposite polarity charge carriers, these hole coming from the positive supply, it is recombining with the electrons. That means this hole and the electron will recombine, one electron will disappear, this whole electron will recombine. That means this positive charge is pushing the electrons to the backward direction, the reverse direction. Because of this, what is going not only this way, this side also. Now this side electrons are entering into the p side. These electrons and the holes, the recombination will take place, and due to the large reverse voltage, now all these some of the electrons they are recombined with the holes. Because of this, the width of the depletion region will become more and more. It is going to increase the width of the depletion region. Now, if the width of the depletion region is more, now these electrons they cannot enter into the p side, and these holes they cannot enter into the n side. Now that's why in case of reverse bias, ideally there is no current flow. ID is equal to 0. ID is equal to 0. Reverse current in the reverse bias, current is equal to 0. How the current is going to be 0? Because in the reverse bias, if you are applying the reverse polarities to the p-type and n-type material, electron hole pair recombination will take place in the p-type region and n-type region. Because of this phenomenon, the width of the depletion region will increases. Now this is the width of the depletion region. Now see the concept here. When the n-type region of a diode is connected to the highest polarity, then the p-type region, then the diode is under reverse bias condition, which results a wider depletion region, the large built-in electric field. Now that's why there is no majority charge carrier movement from n side to the p side or p side to the n side. Remember, diode current I am calling as a current means current is mainly due to majority charge carriers. We are going to consider the current due to majority charge carriers. In case of forward bias, majority charge carriers are diffusing from one region to another region. That's why diode current is maximum current we are getting. In the reverse bias, these majority charge carriers, they are not able to move from the one region to another region. That means there is no movement of majority charge carriers. That's why drain current is 0. This is theoretically. But practically it is not 0. Now why it is not 0? The diffusion current is not there. The diffusion current is due to the majority charge carriers, but a small drift current is there. Now what is a drift current? The drift current is due to the electric field. Now initially at the no bias condition region, a small electric field is there. That is a built-in potential. That is what I said. To cancel out this built-in potential, the silicon diode, now we are going to apply the point just now. Now to cancel the built-in potential, the germanium, that is going to be the 0.3 volts you are going to apply. Above these voltages only, then only the current conduction will take place in the forward bias. Now why this 0.7, 0.3? Because in the open circuit PN junction, due to the recombination of electron and hole, now there is some electric field is present in the depletion region. To cancel out that electric field, this much amount of voltage is required. Now, in this case, in the reverse bias, see, you are applying the reverse voltages. Now see the ions. In case of N side, the positive ions are there. The P side, the negative ions are there. Under the no bias condition, this is the width of the depletion region. Only I am assuming one negative ion at the P side, one positive ion at the N side. For this, I am assuming 0.7 volts built-in potential was developed. Now in the reverse bias, this depletion region went to, this is the size and still the size is increased. In the no bias condition with one negative ion, one positive ion, just I'm giving for the explanation purpose, the built-in potential is 0.7 volts is there. That means here on the P side, three positive ion side, that will increases the electric, more and more electric field will be there. Now due to this electric field in the depletion region, the width of the depletion region is wide. Majority charge carriers they cannot enter from N to P or P to N. But the minority charge carriers they can enter into this region. Holes. These holes, now this side is becoming more and more negative now. Negative ions are there. This is becoming more and more negative, and this side is becoming more and more positive. These minority charge carriers they will be attracted to this electric field, and they can enter into the P side. These minority carriers and coming to P side, they are becoming majority charge carriers. Now, this concept actually you will get the full clarity with the help of whiteboard only, because here I am not able to clearly draw the picture also, because I am not able to annotate perfectly. Now the simple conclusion is In the reverse bias, there is no diffusion current because opposite polarities were connected to the N-type and P-type material. The width of the depletion region is now majority charge carriers. They cannot diffuse from N-type to P-type or P-type to N-type. But there is a reverse saturation current is there that we are calling as a reverse saturation current. That is in the microamperes of current. Even though in reverse bias, a small amount of current will flow. That is due to the minority charge carriers. These minority charge carriers, they will move. That means due to the drifting of the minority charge carriers from the N to P and P to N, the drift current is going to be obtained. The drift current will be in the microamperes. Very small negligible amount of current will flow in the reverse bias. Now this is a simple concept in the reverse bias case. And now see here what is happening. VR1 initially reverse voltage. VR is nothing but reverse voltage. I am assuming my reverse voltage is minus 2 volts applying. For example, minus 2 volts small voltage you are applying. For this small voltage, now see, this is the width of the depletion region, initially two side. If you still increase the reverse voltage to the minus 5 volts, what is going to happen? Still that is width of the depletion region is more and more. That means more and more holes are coming from the positive terminal. These holes, they are recombined with the electron. Still, if you are applying more and more volts, 20 volts or 25 volts, majority charge carriers in the N-type, almost 50% electrons, they will recombine with the holes. Now that's why the width of this depletion region will increase more and more if you increase the reverse voltage case. Now this phenomenon we are calling as the capacitor. Now what is a capacitor? It is a parallel plate capacitor if you take the two string by keeping a dielectric in between these two dielectric material. Now what is happening if it is for VR1? If you take the, for example, my reverse voltage is 1 volt reverse voltage is there for minus 1 volt reverse voltage. The width of the depletion region is, this is the width of the depletion region. There is no charge carriers in this region. Only immobile ions are there. Now it is acting as a dielectric material. Now this is acting as a parallel plate capacitor. Now for this it is becoming one side is more and more positive, another side is becoming more and more negative. Now still if you are increasing the reverse voltage, the capacitance value is going to be increases. That means width of the depletion region will increase and still it is the distance between the two plates also going to be increased. Now that's why the practical application of PN junction diode in the reverse bias is nothing but it is a dependent capacitor, voltage dependent capacitor. Now if you are applying the voltage more and more reverse bias voltage, the capacitance is also going to be increases more and more. The distance between the plates are becoming more. Now this is a simple thing. The PN junction can be viewed as a capacitor in the reverse bias. By varying the reverse voltage, the depletion width will changes, changing its capacitance value. Therefore, the PN junction is actually a voltage dependent capacitor. This is in reverse bias case. The forward bias, it is not acting as a capacitor because the distance between the plates are zero, negligible. There is no distance between the plates. All the majority charge carriers, they are diffusing from N to P or P to N. The reverse bias only, it is acting as the voltage dependent capacitor. How it is acting as a capacitor? Now there is no charge carriers in this depletion region. That is, we are considering that is a dielectric medium. What is a capacitor? It is reporting the dielectric material. Now this is the dielectric material. We still increase the reverse voltage. The distance between the plates becoming more and more, the capacitance being more and more. This is a simple application of diode in the reverse bias condition. Now see here in case of now if you bias in the forward bias, see this conduction band of P type and conduction band of this N type will almost will be in parallel. It is almost, but in the reverse bias, height how much? This much height is. In case of band diagrams, we are calling as a height. The width of the depletion region is very wide. Now this height of this also very becoming high, so that electrons cannot enter into this place and these holes they cannot enter into this side because these valency band holes they cannot enter into this conduction side. This valency band is here. This valence is the conduction band is here for this. This conduction band is here. Now barrier is increased, no diffusion current occurs. Okay, because not sufficient energy to cross the barrier. Drift may still occur. That is what I said. The drift current will be there, small drift current that you are calling as the reverse saturation current. Any generation that occurs inside the depletion region adds to the drift current. All current is a drift current. In case of the reverse bias, whatever the current you are getting, that is due to the drifting of the charge carriers from the one side p type to the n type or n type to the p type. That's why this is a drift current. The current will be negligibly small. That is going to the main problem with this course is the one more problem is there for you people, because parallelly lab syllabus laboratory is there. The ADE lab is also there. Because of not having the classes, physical classes, we are not able to run the labs. Now, after completion of this theory part, if you are doing the first experiment in the laboratory, and even though you are having the small doubts, everything is going to be clear. Now, the main drawback for you people is not having, we cannot run the laboratories and the virtual mode because all the physical devices are there. The physical medium is required. That is the major problem. And explaining with the help of this online mode also, drawing the diagrams, that 100% I'm not able to convey the complete things through the online mode. So I'm trying to deliver the complete content to you people. Now this is the reverse bias case. And now once again I'm revising the three things. The first one is the forward bias, second one is reverse bias, and the third one is the see. Finally summary. Now you read this summary, and because the large text I kept as a summary, point by point, 100 out of 100% you will get the clarity. Now what is the diffusion of the charge carriers? Now this I prepared for you people only, because those who are not getting the clarity with the help of those slides, then you will get the clarity with the help of this summary slides. Okay. Give me 1 minute. I will come back once again. Okay. Now just I will read the points now so that you will get some. Still you are having any confusion about this P and now p-type, n-type semiconductors, I'm making a junction between them. The p-type semiconductor has the acceptor ions. Just now what I discussed, just you recollect the statement fashion. P-type semiconductor is having the acceptor ions. That means the p-type semiconductor the first point is clear. Come to the second point. Majority carriers holes in the p-type and the electrons are the majority charge carriers in the n-type. Now that is for along with the side of the p side as well as the donor side and the n side, which are negatively and positively charged respectively. Now, third one, there will be a difference in concentration, or there will be a concentration gradient of holes from the P to N side, as well as there will be concentration gradient of electrons from N to P side. Now, what is this meaning is there is a large difference between electrons and holes from the N to P and P to N. That means in the P type holes are majority, in the N type holes are minority. That means there is a large concentration difference from the P to the N side of the holes. That is a vice versa for electrons also. Now, whenever there is a concentration gradient, electrons, they will try to flow from the higher concentration region to lower concentration region. This phenomenon we are calling as a diffusion of the charge carrier. Just like whenever there is a pressure difference in the water level between the two places, the higher pressure water will generate. Now that is a simple thing you can clear this. Similarly, because of the difference in concentration of holes, they will start moving from the P to N type and this process. See, in this slide, nothing is there. Is saying about now what is the diffusion, now what are the majority charge carriers in the P type, and what are the minority charge carriers in the N side. Now, if you read this summary, 2 to 3 slides are there clearly, then you will get the full picture in your mind. When you are writing exam also, now you can draw the diagram and you can, with the help of these summary points, now you can get the full clarity. Now, as these carriers, the holes from the left side to the right side, don't call as the left side and right side. The holes are from the P side to the N side, and the electrons are from the N side to the P side. Now there will be recombination of charge because holes will recombine with the free electrons, and electron will be recombined with the free holes. Whenever these electrons are they're crossing the junction, during this process, electrons and hole recombination will take place. Because of the recombination of these charges, the ions, that means the acceptor ions on the P side and the donor ions in the N side, they will be now surfaced out. That means there is no charge carriers. Surfaced out in the sense they are not covered by the any electrons. Because of the recombination of holes and electrons, these charges of the ions now become uncovered. That means along with it there are no charge carriers. In the depletion region there is no charge carrier. There are no charge carriers. There are now uncovered negative charge on the P side and uncovered positive charge on the N side. This is why these bound negative charge on the P side and the positive charge on the N side. Now the region where there will be no mobile charges that you are calling as a depletion region, or other name of the depletion region is space charge region. Now 3 conditions. Under the open circuit condition, the depletion region contain only immobile charges. Just if you read with focus, then you will get the full picture in this slide. Now these immobile charges are forming two layers. Negatively charged layer on the left side, that means on the P side, positively charged layer on the right side, that is nothing but your N side. Now a potential is developed and the potential is a positive on the right side is nothing but N side, and the negative is nothing but the left side. Now if you consider the same diagram here, now this you read it. Now the holes cannot, now see what is going to happen. Now these holes in the P side, they cannot cross over the junction and come to the N side because this will be the positive potential which is developed. Now this is called the barrier potential. Now here the barrier potential will be developed in the depletion region. As well as the electrons cannot move from N side to P side because these bound negatively charged layer, that is preventing, that means the barrier potential is preventing to move the electrons from the N side to the P side. Now this potential is creating the field. Now this electric field, that only we are not able to move electrons from the N to the P or holes from P to the N side. Now this you read this. Now the last slide you are having, in case of forward bias and reverse bias is also there. Now just read this summary, then you'll get the full clarity about the PN junction diode. Okay, this is the complete picture about the PN junction diode. Generally in the physical class, it will take only 2 minutes of time. But even though even I'm taking the 1 hour time, but still some little bit this thing will be there because of not able to draw the pictures completely. But read this presentation thoroughly. But at the end of this class, I will share these presentations to you people. I will take the CR's mail IDs from the coordinator ma'am. I will share this presentation to you people. Whenever after completion of the class, just to go through that PPT, then you will get the full picture about the topic. Now this is what we are going to what I plan to discuss today. That is the PN junction diode. With this, I am stopping the today's class, and now we will start the today's quiz part. Okay, shall I start the quiz today? Today's quiz? Right. Ma'am, start the quiz, today's quiz. Now the time is 3:47, and now we are giving the today 10 MCQs are there. Now we are giving you the 20 minutes time because the next followed by one more class is there. Now we'll stop the class at 4:05. That means 57 and the 20 minutes we are giving to you people. And now start your test. Your quiz was started. Now all of you take the quiz. The last class, some of the people they are not submitted your quiz. For those people, we are not given the attendance. Today, within the time, within 20 minutes time, try to submit your test. Then only you will get the attendance.